the president of the AAPG Young Professionals Peru Chapter. And first of all, I would like to welcome all the audience from Peru, from the rest of Latin American countries, from North America, from Europe, and so on. Not only on behalf of our association, but also of the AAPG Peru student chapters from Tacna, Arequipa, Cusco, Piura, and the Universidad Nacional de San Marcos, and the Universidad Nacional de Ingenierías from Lima. All of them have organized this webinar with us. Additionally, I want to thank also to Atentamente Peru, who is collaborating with us with their streaming platform to provide the best experience in our webinar. Thank you so much to all of you guys. The Young Professional Chapter of the American Association of Petroleum Geologists of Peru is a group that aims to promote and disseminate geoscientific knowledge to students and young professionals in the energy industry. As part of the goals set for this year, the chapter will organize a series of courses, talks, webinars, and so on in order to promote research through continuous training. In this opportunity, we have the great satisfaction and pride of having one of the founders of Trustwell Imaging. Thank you, Rob Vestrum, for accepting our invitation to participate in this webinar. We really appreciate it. As I said before, Rob Vestrum is one of the founders of Trustwell Imaging, a geophysical service company that focuses on seismic imaging in mountainous areas. He holds a bachelor in geophysicist from the University of Alberta, a master's degree, and a Ph.D. from the University of Calgary. He was an early developer of foothills and isotropic depth migration, which began at Shell in 1996 and further developed at Kelman in 1997 and at Veritas in 2001. Rob's depth imaging project experience covers the foothills of mountain ranges, including the Andes throughout South America, the Carpathians, Himalayas, and the Zagros Mountains. Recognition of Rob's pioneering work in TTI and isotropic imaging includes the John Kendall Doctorate Thesis Award from the Faculty of the Science at the University of Calgary and the CEGS J. Clarence Karcher Award for significant contributions to science by a young geophysicist. Today, Rob will share with us the webinar titled Geologically Constrained Seismic Imaging of Complex Structures. And here we have a brief summary of the webinar. Seismic data in Trustwell settings is limited in data density because of the cost of field acquisition in mountainous and foothill areas. Variable surface conditions, from solid rock to loose scree, results in low signal strength and high noise on the seismic recordings. In addition to these geophysics difficulties, the geology tends to have a high structural complexity. Overcoming these compounding issues requires tight integration between the imaging geophysicist and the structural geologist. Fortunately, geologic constraints can improve the seismic imaging, and experimentation with subsurface velocity structure can bring seismic constraints to the structural geology interpretation. In the ideal case, the positive feedback loop between these geoscience specialties will also result in improved seismic imaging. Seismic data is recorded in time domain, and depth imaging is far more than a simple vertical scaling to calculate depths from the reflector times. Depth imaging corrects for a myriad of wave propagation effects that results from a structural complexity of subsurface lithology. The more accurately we might correct for these wave propagation effects, the more we may improve the coherency and clarity of the seismic image. Depth migrating with a geologically constrained model often results in improved seismic imaging below geologically complex structures. Seismic data examples ranging in style from a simple monocline in the Andes of Peru to a near vertical carbonate bedding above the structures in the Zagros Mountains show how building geologically constrained structural models for seismic depth imaging results in optimized imaging and reduced exploration risk. Surface geology maps and regional cross-sections are the foundational elements for building a truss belt depth imaging velocity model. Where wells are available on the seismic data volume, it is extra helpful to have the fixed points of formation depths to calibrate the velocity model such that the seismic reflectors depth match the depths to the correlated well depths. The calibration process will often result in improvements the continuity of imaged reflectors in addition to the improvement in accuracy of reflector depth. Just to remark some things before this presentation, the presentation is going to take approximately from 35 to 40 minutes. So at the end of the presentation, you are going to have the opportunity to write down your questions on the Zoom chat. So in that sense, do not hesitate to ask anything. So, and one additional thing, please, I encourage you to keep your microphone and your cameras off during the presentation so as not to interrupt the exhibitor, okay? So Rob, welcome again, and we are ready whenever you want.
Thank you very much for the kind introduction. And I guess I'll start sharing my screen. Desktop one. And thank you very much for this opportunity to talk about my two favorite subjects, structural geology and seismic imaging. The thing with the reason I love structural geology so much, other than its inherently interesting topic to study, is the understanding of geological knowledge and understanding the structural geology is a key constraint to seismic imaging of complex structures. And so my theme here is the integration of geologic and geophysical data is essential to optimize seismic imaging in complex structure areas. So that's where this positive feedback loop between the two disciplines. So I'm going to talk a bit about the seismic illumination and some of the problems we face with seismic imaging, and then I'll show you some examples of the model building process and how we use geologic constraints to build a subsurface velocity model, and show you some data examples from Canada, from Colombia and Peru. First, just a comment about the theory and practice in structural geophysics. In the areas we work, it's sometimes the theory doesn't always match what's practical, and theory is really when we know everything, we understand what's going on, but nothing seems to work. And in practice is when everything works, although nobody knows why. Now, in geophysics and complex structure is really where theory and practice meets. Nothing works, and nobody knows why. And that's really the issue here, is we're quite under constrained in our seismic imaging problem. Now that was actually a joke, and that's the unfortunate part about not meeting in person. I don't get to hear people laugh, and I don't get to see who is sleeping. So that's I will just have to take it as assume that you thought that was funny, and that you are going to stay awake during my presentation. Okay, so on to the meat of it. We're going to look at this wave as it propagates into the subsurface. We've got this overthrust geometry here in this cross section. The color corresponds to the velocity. The warmer colors are higher velocity. The cooler colors are low velocity. And you can see this little dot over here. This is the source location. And we're going to watch this wave as it propagates into the subsurface. And it's going to reflect off of these subsurface reflectors. Here, this is the target reflector down here in the deep section. And we'll see how the wave behaves as it propagates down this fault point. So we can see this wave propagating down. The wave field is bent, where the higher velocity and hanging along, there's a reflection. We'll also see another reflection coming off of the deeper target reflector, and it's going up and through the overburden and to be recorded up at the surface. I'll highlight this. My cursor is not working, but okay. So I will highlight this this wavefront as it comes up to and approaches the surface, and you can see the energy is going to arrive at the surface first, below the fault, and it's going to arrive at a time later over here in the foreland. And that's because the wave is propagating at a lower velocity over here, so it's traveling a shorter distance, and in the same time, and we travel a greater distance in here. And what we really want is we don't want this reflection energy that we record at the surface. What we want is an image of the subsurface target, because that's what we want to find. In the seismic imaging problem, as we record the reflections at the surface, but we don't know where in the subsurface that energy came from. And what we really want is the position of the reflectors. We want an image of the subsurface, but we need the velocity, understanding of the velocities in order to determine that. So I'm going to talk a little bit about seismic illumination, because it's a topic we don't really address very often, and there are a lot of problems that we encounter that I think are interesting to look at. When we record seismic reflection data, we don't know where in the subsurface that reflector energy originates. We need to know the velocity structure of the subsurface to image the seismic data, but if we already know the subsurface structure, then we don't need the seismic data. So we always start with a limited knowledge of the subsurface, and we need to get ourselves into this process where we're trying to image the seismic data. And as we improve our imaging, then we improve our understanding of the subsurface structure, and then we can improve the imaging further and hopefully get this positive feedback going between the disciplines. What we really need in order to get this optimized seismic image is a regional geologic understanding to constrain our velocity model, and we need to understand how waves image the subsurface. So I'm going to show you a movie here that basically I developed to describe the process of reverse time migration, which is a type of seismic depth imaging. Even though it's called reverse time migration, it's actually a depth migration. And what the process is, I think, is reasonably intuitive to watch this process happen, because we can learn a little bit about how we illuminate the subsurface. And how the process works is like this. So we have the source of source location, and then we propagate the energy to the subsurface as though we were shooting a seismic source at the location, and we fill the subsurface with this source energy. And then we can backward propagate that energy in reverse time. And the reason for that is that we can cross correlate with the receiver wave field. So the other thing we do in reverse time is that we backward propagate the energy that we record. So the energy that we record at each receiver location, we take that and we propagate that into the subsurface, just like we do this source spike. And then whenever we have a source energy and receiver energy at the same point in the subsurface at the same time step, then we've met the imaging condition and we have a seismic reflector. So if we have source energy and receiver energy in the same time and space of the subsurface, then we have a reflector. That's the position of our reflector, and so then that's this reflector here. Now, let's just watch this happen. And we try to meet this imaging condition where a reflector exists anywhere that the source and receiver wave field have energy at the same time and space. So to kick off this movie, we can see the wave as it propagates in the subsurface. It's refracting, it's bending and distorting. There's all kinds of things happening to the wavefront according to the velocity model. Now, this is synthetic data, so everything's pretty idealized in terms of when we migrate it, we should get the exact same image back out. But again, I find this a good illustration. So now what we're doing is backward propagating this in reverse time, bringing the source energy back. At the same time, we're downward propagating or backward propagating the receiver energy. This is what we recorded. This is the energy we recorded at these receivers. We're sending it into the subsurface. Down here, we're creating this image as we go, as we cross-correlate the source and receiver wave fields. So this is now what we've seen here is the creation of this migrated shot gather, and we can see how this shot is imaged different reflectors in the subsurface. Um, so this is just for one shot, and so we obviously need to use many different source locations, many different sources to image the subsurface. So that's where this movie will be useful, is that we can see how each time we create a migrated shot, we add that up into these final stack section, and we create a migrated section. And this is useful because we can look at how the structures, these different structures get illuminated. So these are individual shots on the top movie. The bottom movie at each step is that each source gets summed into the final image. So you can see we've got these sources that are coming down into the valley, and now they're starting to image these structures over to the right. And as the source moves to the right, we can image these other reflectors in the syncline, and then far enough to the right, we get the illumination of this left side of this syncline. And then as the source moves over, we can see we're imaging these other complex structures over on the right. Now, like any scientific method, it's interesting when things work out, and this is obviously a very idealized case with synthetic seismic data, and everything is working perfectly. We get the image that we modeled in our synthetic data. But what is always much more interesting from a scientist's standpoint is what happens when it doesn't work. So let's look at this image over on the right of this lower image. It's imaged just beautifully. We've got this structure. It's hanging wall anticline, fault plane reflector, and the footwall syncline, although some of the footwall syncline is missing. So then if we could zoom in and look a little more closely at what's happening over here, you can see that there are several reflectors here that we have just not imaged. And the reason for that is this illumination problem. We would need to have the line be shot much longer in order to have source and receivers over here off the line in order to image this reflector. So if we had a source and receiver off to the right over here, then if we shot that source, we could get a ray path that's going to image this reflector. So this is an aperture issue, and it's an issue of illumination because we need to have the line shot longer if these steep dips at the end of the line are important. And you'll see this in seismic images all the time, where as you get to the edge of the data set, we start to lose steep dips, and we start to lose the dips in particular that are dipping towards the edge of the line because we haven't had source and receiver to illuminate those details. So on the subject of illumination, this is a bit of a side topic, although an important one. It comes up all the time for us, and it just came up last week. So I thought I would throw it in here on the topic of illumination. And that's when we try to tie 2D lines in complex structure, sometimes you have this illumination problem. And the problem results from the reflection energy that may be coming from out of the 2D plane. Every reflector may not tie depending on the dip orientation. However, understanding the 3D problem will help us to correlate those reflectors. So I'll show you how that works. This is a seismic line from Peru. It's a real beauty. We've got this lovely hang wall anticline, some nice folds in it. Here is the fault plane reflector coming down here, or coming up to the right. And here's a bit of the footwall image at the bottom of this bottom of the slide here. And you can imagine if we had a strike line running down here, we might see that energy coming from out of plane. Now, this strike line is pretty close to the crest of the structure. Imagine if the strike line was over here to the left, we would definitely have a significant problem with out-of-plane energy. So we're here close to the crest of the structure, but even still, the imaging of the data along the strike line is going to have ray paths that go over to the right. So if we have a vertical line, so we assume that our seismic data set is vertical, when we shoot these 2D data sets, but the energy could be coming from out of the plane, in this case, over to the right. So when we go to overlay the strike line, so this is the strike line now, this is at 90 degrees to this data set. I've just laid it down here flat so you can see it. And at the intersection points and through here, you can see, even though it's only a little bit out of plane, the reflectors on the dip line are a little bit higher than the reflectors on the strike line. And then, sorry, my apologies, I've got that backwards. So the reflectors on the strike line are a little bit higher than the reflectors on the dip line, because the dip line is imaged at further up dip, and the strike line is imaging it from out of plane. And that mist tie, so we're oftentimes asked as a processor to fix this mist tie and shift this data. But you can see there's a fairly small shift in this upper reflector and a pretty significant shift on a deeper reflector. And this fault plane reflector needs a very large shift in order to be in the right place. And the footwall reflector doesn't look like it needs much of a shift at all, because it's horizontal, and so it's imaging within the plane. So what we can do, if we have this dip line and the strike line with these mist ties in the middle, because we've imaged out of the plane, all we can do is, like in PowerPoint here or on a piece on the paper displays, is that we can rotate the seismic data until it matches up with the angle normal to the reflectors on the dip line. And you can see actually this out of plane energy is now correlates between the strike line and the dip line, and all the way down the section we've got a correlation between the dip and the strike line, even this deep reflector. And the reason the deeper one is just so far over is so far shifted is because of the out of plane issue at an angle becomes much larger the deeper you go. Now we've kind of lost the correlation between the footwall and the between dip and strike lines, but we have the correlation of the dipping reflectors. So this is something that, like, I'm not sure how one would fix this in interpretation software. If you could have your, if you could take a strike line and not display it vertically in 3D, but maybe have it displayed at an angle, and then have it come down in this sort of way, so you could make a map in 3 dimensions. But the one thing that you can do in this case is use this as kind of a jump tie. So you can correlate this reflector on this line, and then make the correlation to the strike line. Follow this reflector across the strike line to the next line, and do the same rotation to get the correlation onto the next dip line. And then you can be confident that you're going from one line to the next, using the same reflector as we go across the block, with using the strike line. But obviously, if you have you can't really use the interpretation on the strike line in the map, because there will be a discontinuity in the strike line. Anyway, so that's an interesting, a significant, and a rather common problem in thrust belt exploration, is this illumination issue that results in a misalignment of the reflectors between the dip and the strike line because of out of plane energy. Okay. Now let's get into the meat of it all, the model building for depth migration. What we do is we interpret the subsurface velocities to optimize the seismic imaging. And we don't trust the machine to do our velocity analysis for us. We believe more in the human mind, and be able to take in all of the information, and the professionals involved, the geophysicists and the geologists working together to get the most out of the seismic data. So velocity model interpretation for depth imaging, what we do is we have this interpretive interface to draw the velocity boundaries. So this is our cross-section down here, and we've got our velocity boundaries. And then we display rays to show where we illuminate the subsurface. So that we've got the imaging point in the subsurface here. And we can see the rays as they propagated through the near surface and where they have bent and curved at the different velocity interfaces. And then we can also see here the redundancy inherent to our seismic imaging, which really helps with our velocity analysis. The image gather display then indicates potential velocity changes. Now here is where we can see some of the problems with our seismic data. Like in the marine seismic data case, where we can use a lot of these automated methods to let the computer statistically come up with a velocity model through reflection tomography. We don't really have the luxury of having a lot of water above our first reflector. We've got geology right up to our recording surface. You can see on the image gathers. So these are image gathers that for imaging points around this wave. Offset is increasing to the right. So the near offset is where the source and receiver are close together. Far offset is out here where the source and receiver are far apart. And so then these combine, we can sum them together to make the seismic image. Now, the velocity errors, so the velocity errors will result in our reflector being too deep or too shallow. And the longer ray path of the long offsets means that our velocity of the long offset is going to be even more, have a greater error than the near offset. So we'll have smiling or frowning on the far offsets. So what we want is the same reflector, the image at the same at all depths. And then we can, so in the image gathers flat, this event in the image gathers flat, so we can be confident that our velocity model is accurate. Now, notice that there are several reflectors we could interpret on this section, and yet on the image gathers, there are only 2 or 3 of these reflectors that we can use for velocity analysis. Now, we can see as humans that looks pretty flat, and if we saw some curvature down or up, we could identify that and say we need to have higher or lower velocity, and then make a new interpretation based on that. But we don't trust the computer to come up with all of these layers and this kind of structural detail based on these few events that we can see on the pre-stack data. Also, the near surface is the lens through which we see the subsurface. So we've got all these different surface conditions, and we can have significant laterally varying velocity in the near surface. However, the near surface is where we have the least amount of offsets. We have very low fold, very low amount of redundancy in the near surface. So we really don't have that much information to work with. So we've got low data density, low signal to noise, and high structural complexity. Even this data set here is actually very mild compared to our usual, much more structurally complex data set. And in which case the problem becomes significantly worse. So we want to build our geologic model to come up with our subsurface interpretation. So we built a structural model, and in this case, interpreter collaboration is the key. So we base our velocity model on structural geology. So we have this, we build a geologic model based on the studies in the area. So surface geology, any studies from wells, any cross sections, balanced cross sections, and anything that the geological studies are based on are good information for us. Any sort of regional perspectives are really important for us to understand the subsurface structure. And we use the velocities corresponding to individual rock units. With time migration, we're averaging through the near surface, finding an average RMS velocity to each reflector that's going to optimize our image. But in the depth imaging case, we expect our velocity model to tie and correlate with the geology, and then we keep the velocity consistent unless we have a good reason to change the velocity within a rock unit. The section gets more sandy in a regional perspective in one area versus another. We might change the velocity within the rock unit. Otherwise, we would keep it the same. And then we consider the model scale that affects the travel times. So thicknesses, on the order of 200 meters or more for rock layers, what we want is we want to think about as our waves propagating, and the wavelength effects happen over several seismic wavelengths. So a unit that's 50 meters thick, even if it's fairly strong velocity contrast, is not going to affect the seismic wave propagation significantly. So we combine multiple layers together, represent them with gradients, and, um, and go that way on the larger picture. I'll show you an example of that in case history at the end. Okay, the sensitivity of imaging to model velocity decreases with depth. So really, like I said earlier, the near surface is the lens through which we see the subsurface. And so it's really important to have that near surface nailed. And as we get down to the target level, of course, the shape and size of the target is very important to the interpretation team. It's just not as important to the depth imager because all of the wave propagation has happened already by the time it gets down to the target level. And so then the velocity is not, the imaging is not very sensitive to velocity in the deep section as much as it is in the near surface. And then we test model scenarios based on seismic diagnostics and our interpreter and geologic input. So the workflow is pretty simple. It looks like this. We've got our inputs in orange on the left. We have the interpretation, the most important thing to the whole process. And we need that at the start, so really good pre-stack time migration, and then an interpretation of that section to get our velocity model. And then we have the input process gathers, and from that we can migrate the data. Now migration is simply we're mapping the data or moving the data from where the reflectors are recorded to where the reflection energy is recorded to the geometry of the reflectors. So from reflections to reflectors. So what we want to do is move the data to where the seismic energy originated. So that's going to give us the shape of our subsurface structure. And that's basically what migration is all about. And then we ask ourselves these tough questions. Have we optimized the image? Do our wells tie? Does our depth image compare very well to the pre-stack time migration? Or is the imaging much weaker than the pre-stack time migration? So when we ask these tough questions, typically the answer is no. If we have wells in the area, maybe our reflector is deeper than the correlated well depth. Maybe the image gathers are not flat. Maybe the imaging is not as strong as it is on the pre-stack time migration. A lot of things can go wrong, and they do. So we say no, and then we go back and revise our interpretation. And we say, okay, well, what can we do? Do we need more carbonate in the hang wall of the thrust to get higher velocity? Do we need to change the geometry of the syncline? What do we need to do to get higher or lower velocity in the model? And then we build a new velocity model, and we migrate again, and then we ask ourselves these tough questions again. And we keep going around this circle, maybe 6, 8 times, maybe 10 times, until we can start to say, yes, whoa, look, that seismic reflector matches very well with the correlated top as well. We've got some pretty flat image gathers where we can see data on the pre-stack data. And we've got lots of details that we don't see on the pre-stack time migration. So then we can say, yes, we break out of this loop, thank goodness, and get to the place where we can do a little bit of last-minute cleanup of the data, a bit of residual move-outs, apply a bit of a coherency filter. We have a Colombian client that calls this the makeup. He said put a little bit less makeup on the section, just the kind of cosmetics, another word for it, and so we get our final seg-wide volume, and then off we go. So it's really quite a simple process, really. Okay, now I mentioned seismic anisotropy. We build all our velocities considering seismic anisotropy. So just as another aside, I'm going to talk a little bit about that. That's actually my area of expertise traditionally, my educational background. And it's challenging enough to think about subsurface velocity structures and the velocity varying with rock type and over the cross faults and synclines and anticlines. But now we also need to think about managing the velocity variation with depth. So velocity variation and spatially and with depth and also with direction. So the direction of wave propagation also affects the velocity. Um, and I'll show you how that works in practice here. Here's an example of we're going to compare a presec time migration to presec isotropic depth migration. So where we correct for the refraction effects, but we're not correcting for seismic anisotropy. And then we're going to look at anisotropic depth migration, where we correct for both lateral velocity heterogeneity, so the refraction effects, and seismic anisotropy. So this presec time migrated section, we've got robust imaging all across the section. The advantage of presec time migration is that we can average through a lot of effects in the near surface by picking RMS average velocities that optimize the image for each reflection. What we've got here is an overthrust, high velocities, older rocks thrust up over younger rocks. And here is a producing field here circled by the blue. And we've got a really nice image of this anticline inside the blue circle. And over here in the green circle, we've got this this duplex system. So we've got 1, 2, and if you look just right, there's a third imbricate over here on the left side of that circle. Now, that's with presec time migration, so averaging through these various effects, but not really correcting for the ray bending that we have that we encounter with velocity variation. Whereas isotropic depth migration corrects for this ray bending below this fault, and you can see we've got an improvement in imaging in this duplex system here. We compare back to the. I can't go back. So I need to figure out how to go back. Oh, there we go. Okay. So if we go back to the presec time migration and then forward to the depth migration, we can see the imaging sharpen and get into focus where we can see these three imbricates much more clearly in here than we could before with the time migration. However, the base of the syncline is a bit broken up, and this structure in the blue is actually gone. And this was the big frustration of depth migration is because before we started correcting for seismic anisotropy, big frustration was is you could fix one thing on the image, but something else would break. And that's what's happened here. The green circle is fixed, it's better, but inside the blue has broken, and we don't have the structured image anymore that we had imaged nicely on the time migration. So then what we did is we started correcting for this anisotropy. So we've got these dipping rocks, and the rocks are varying significantly in dip in the near surface, even though it's not very much velocity variation. It has a big dip variation across the syncline. When we correct for the anisotropy in this syncline, we can image all the way through the base of the syncline and heal up the base of the syncline. We also heal up this structure here. So this is this lateral position change, and I'll show you how that works in a minute. We have this lateral position change on the right side of so the image on the right moves left, the image on the left moves right because of the dip and the overburden. And so with that, the base of the syncline actually heals. Notice also that we haven't broken the image inside the green. If we look at what's happening inside the green circle, we've got this lateral position shift, and it also sharpens up the leading edge of these structures, and the imaging becomes stronger on the limbs of this duplex system. And this actually looks fairly similar to the TI logo. That's not a coincidence. So let's look at how that seismic anisotropy thing works. So this is not from the Andes. This is actually from Canada. It's west of Calgary. Once this is all over, you'll have to come and visit and see the Canadian Rockies. Um, and so what we've got is we've got these dipping intermittent sands and shales. The layering is smaller than the seismic wavelength, and so the rock is more, less compressible in the direction parallel to bedding. It's more difficult to squeeze it this way, and it's more compressible in the direction perpendicular to bedding. So uh, we end up with a higher velocity in the direction parallel to bedding, and a lower velocity in the direction perpendicular to bedding. And that results in, it's reasonably intuitive to look at these arrows here, but what's interesting is the shape of the wavefront as it propagates from this location into the subsurface. The point of deepest penetration of the wavefront is not directly below the source location, but it's shifted laterally over from that position over to this position here. So we have this skew to the wavefront, and this is how we get this lateral position shift that we saw on those seismic images. So I've got a movie now to illustrate this problem. So we've got the energy is propagated along the direction parallel to bedding, and it's gone a greater distance in the high velocity direction and a shorter distance across the layers in the low velocity direction. Imagine if you were driving across a farmer's field and it's been freshly tilled. So you've got these rows running this way. If you drive your car or your truck or ride your bicycle, mountain bike in the direction parallel to the ridges, you'll be able to go very fast. So you'll just be able to stick your tires in the grooves and go fast. If you go this way in the direction opposite the furrows of the ground and you bump, 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 and you go really slowly. It'd be a rough ride on your mountain bike and a rough ride in your car as you go across these bumps. And you travel at a shorter distance. In the same time, you travel a shorter distance because you'd be going at a lower velocity across these bumps than you would be with the bumps. And the same sort of thing happens with layering as the wave propagates into the subsurface. So that's reasonably intuitive. What's more interesting, I think, is the side slip effect, where if you're pointing your bike or your truck downwards, every time you hit a bump, you're going to bounce toward the high velocity direction. And that's how this energy ends up over here. The point of deepest penetration of the wavefront, it must be some summation, some motion that's normal to the wavefront going straight downwards, but also some motion that's tangential to the wavefront in order for the energy to arrive here. So it's not just moving normal to the wavefront anymore, it has this kind of side slip effect as it goes into the subsurface. So let's look at this wave as it propagates in the subsurface, and then it impinges on the interface here. Now, when it goes to reflect, the Snell's law governs the direction normal to the wavefront, the phase velocity, and so as this energy reflects, it reflects straight back upwards, and then the side slip also is going to go in the opposite direction. So if we turn around and we're heading across the farmer's field again, we're going to bounce toward the high velocity direction again. So what we'll see here is the wave propagating back up to the surface, and the side slip is also in the opposite direction. So this is the energy you see. Energy propagates down, reflects, and comes back up to the surface. We have recorded that energy. We have a reflection that we've recorded over here, but if we ignore the anisotropy and we have a horizontal reflector, we might assume that energy came from over here, and that's how we might process our data. So that's what's happening in this case here when we go from isotropic to anisotropic, from, pardon me, isotropic, sorry, to anisotropic depth migration. We're correcting for the side slip effect. And that's why you see the shifting in the syncline, everything on the right side of the syncline shifts left, everything on the left side of the syncline shifts right, and we heal the base of the syncline. We also connect the energy inside the blue circle much better. And over on the right, where we have the dips are down to the left, we have the side slip is correcting for this lateral position problem by imaging on by shifting it into the proper position. And depth migration is by its nature a very delicate process. As you can see from this example, we ignored the anisotropy and the imaging broke down. So if we have two different velocity models and one shows an improvement in imaging, then we can be more confident that that velocity model is a more accurate representation of the subsurface. So I'm running out of time. I just have an example, 3D velocity model building for 2D imaging. Um, I'm so keen about human input and collaboration, but sometimes relying heavily on human input is labor intensive and can lead to some inconsistencies through a data set. So this is an example. This is from Peru, depth migration project, and there were multiple lines, and trying to tie the dip and the strike lines together. And it's really quite simple. One could say it's a piece of cake. I tried to find a Spanish expression. Maybe something you could say you could do with your eyes closed. It's very simple to make a velocity model to match between different strike lines. That seems really simple, but when you have many data sets to work with across an entire block, it's a lot of velocity models to build, so labor intensive, but also potentially error prone. There could be some inconsistencies. And this is the problem we decided we had with in the hanging wall of this thrust as it came to surface, is that we couldn't quite get this perfectly consistent all the way across the block. So we started building, after this project, 3D models to image our 2D seismic data sets. And this is another project, also from Peru, this kind of monocline type of structure. And we built this three-dimensional model with 3D horizons in order to get consistency across the entire block. So this is basically a geological constraint we used is that we wanted to have the same rock layers in 3 dimensions with this consistent velocities across the block. And we also want to have our dip, as I showed you with the TTI anisotropy, we want to know the orientation of bedding, so we know the direction of the highest velocity, and we use the horizons to come up with that TTI anisotropic dip. And here's the example: time migrated image and a depth migrated image. We've got we've got some pull up, so to show the velocity model. We've got more low velocity on this side of the monocline, more high velocity on this side. So then the deeper reflector is going to have this pull up as it goes across and is lifted up onto that side. And we can flatten that out with the accurate velocity model for depth imaging. And we can also get a little more in detail in the deep section and a more consistent interpretation through these details in here. Now we do lose some of these steep dips, and this is also an illumination issue. If we have a very steep reflector in here, then we're going to see these long rate path lengths that are going way over to the side. We're also going to have limited offset. In terms of our offset range, one could imagine if we get to just a few hundred meters of offset, then the rate path is going to be off the end of the line. And it's going to be very difficult to get a lot of redundancy and stack power into that image. If this forelimb is near vertical, the rate paths are shallow and long, so illumination is weak. Okay, here's my case history. I apologize for going over it, and I promise this is an interesting data set. Are we okay for time?
Yeah, we are okay.
Okay, thank you. Okay, so this case history, I just want to show a seismic data set in the foothills of the Colombian Andes. We've got high single noise seismic data with strong RTM results in the stronger signal areas, but Kirchhoff preset depth migration is more robust in the area of higher model certainty. So how I break down when I think about the different categories of seismic imaging algorithms, PSTM, I'm thinking about Kirchhoff preset time migration. It approximates near-surface complexity with average velocities called RMS velocities. Those RMS velocities may not make geologic sense because they're averaging through a lot of effects in the near surface. However, it's a robust method that takes very little a priori knowledge of the subsurface. And we can always get a basic image because we have this freedom uh, in our velocity field. With PSDM or Kirchhoff pre-stack depth migration, it corrects for refraction and anisotropy effects in the layers above the target. It uses interval velocity model. It should correlate. We expect this to correlate with the geology. It's a geological model. It's more delicate than pre-stack time migration, so inaccuracies in the velocity model results in a weak seismic image. So that's a downside, and also a plus because then if we have two different velocity models, we can see how the imaging is improved or degraded to decide which velocity model is more accurate. Reverse time migration, despite the name, RTM is a depth migration. Like PSDM, with the added benefit of correcting for more dramatic velocity variation. It's even more sensitive to velocity errors than PSDM. Now, RTM is rarely applicable in our thrust belt areas. It really needs these three criteria. Strong velocity inversion below a dipping interface, such as subsalt, which is the primary application, or below an overthrust. If we have high signal to noise on the seismic data for wave field reconstruction, and we need that as a requirement. And we also need low uncertainty in the velocity model. We need our velocity model needs to be accurate in order to really optimize the imaging. These criteria are common in subsalt marine environments, but it is rare to meet all three in a complex structural land setting. And we thankfully have that in this data set, although the imaging improvements are subtle. So this is a geologic setting. We're in the high plains of Colombia on the leading edge of the foothills of the Eastern Cordillera. And we've got these complex structures in the subsurface. This is interesting to see the detailed interpretation of these deeper rock layers where they're on target intervals. But of course, we would average through these layers for depth imaging. As you can see on this velocity model, we just average through these intervals to get to approximate the velocity variation and the anisotropy. The numbers represent the velocity at each grid point, and the numbers are oriented in the direction parallel to bed, so that we can see the dip in the velocity model. So this represents the velocity normal to bedding, and this is the orientation of the bedding is parallel to the number, so you can see how this goes through the subsurface model. Here's the PSDM image in depth, and I'll show you we're just going to zoom in on this and then compare back to the time migration. Here's the legacy PSTM. You can see we've got good signal to noise and quite strong imaging throughout. You can see the major features. We reprocess this in time, and it looks a bit overcooked in the shallow section, but we've optimized our coherency to bring out the details in the deep section. And so we've got more detail and stronger reflectivity in the deep section, but it does look a little bit overcooked, shall we say, in the shallow section. Now, comparing this to the depth migration, I scaled the depth migration back to time for ease of comparison. Notice that this syncline, we really couldn't image the syncline very well with time migration because of this variation with a velocity with direction. And of course, the dip is changing dramatically inside of a syncline. So we can't really average through that effect very well with pre-stack time migration. So we needed the pre-stack depth migration to image that. We've also got much improved imaging in the footwall, and this deeper anticline also shows an improvement in imaging with the Kirchhoff depth migration. Now, in the footwall, that's where I'll draw your attention right now, as we compare it to the reverse time migration. With the RTM, I believe it's a lot easier to follow the reflectors from the foreland side in through the up to the footwall of this thrust into the footwall syncline. It's easier to follow the correlation through here. With the Kirchhoff, um, it's more difficult to follow the reflectors from foreland up into the footwall. And in this under the base of the anticline, you can see we've got also improvement in imaging with the RTM because of these, healing the different wave propagation effects through this dramatic variation in the surface. So we can see this side of the structure is imaged a lot better with the RTM, and this deeper reflector is also improved in imaging. Now let's have a look over to the west end over here, and this is where we've got much more challenging imaging on this side. And the Kirchhoff depth migration shows these steep dips that correlate with the surface geology. So we've got some improvements there that we haven't really imaged very well with the pre-sec time migration. So a difficult time with the complexity over here. And the depth migration, the Kirchhoff has actually imaged this a lot better and gives a good perspective of this deep target down here, which is a little more difficult to image on the top. Now the RTM, because of model inaccuracies and low signal to noise, the RTM is broken down. So the RTM does not show a very good image because of the low signal to noise for the wave field reconstruction, the high model uncertainty, and we don't really have the velocity variation that RTM is required to fix. That we don't really have that geometry. We don't have that problem to solve, I guess is what I'm trying to say on this end of the survey. Okay, the slide that you've all been waiting for, the conclusions. And then I'd be glad to take any questions and have some discussion going. The interpretation input and geological constraints are important for optimizing the depth imaging velocity model. Collaboration with structural geologists and understanding the regional geologic setting is essential for imaging success. Beneath the complex velocity structure with strong signal, the deeper events improved in coherency and geometry with increasing improvements in imaging technology. So we go from pre-sec time migration to pre-sec depth migration and to RTM, and the imaging improved each time in the complex area with strong signal. But the RTM broke down in the area of model uncertainty. And that's the thing we find is that we have an increase in both accuracy and sensitivity as we go from PSTM to PSDM to RTM. And that's all I have to show you. I'm sorry I'm 10 minutes over, but I hope you still have energy and have some questions.
Thank you, Rob. Thank you so much for your detailed presentation and for your time. So now we are going to pass to the question block. Okay, so I'm going to read the questions for you. Okay, let me just give me some minutes. I'm going to find the questions. Okay, here we have the first one. What do you consider are the main advantages of using RTM compared to other methodologies?
The RTM is like I say, it's a rather specific algorithm because it'll when you have significant wavefront propagation effects, like a big velocity decrease across an interface, in particular if it's a steeply dipping interface, then the ray tracing for Kirchhoff tends to break down the diverging rays and that type of thing. Has a real problem with imaging below a large velocity inversion. And an RTM does a much better job because you've got the big thing it has with Kirchhoff, we have this kind of infinite frequency approximation where it's shooting these rays and we have a single sample. Whereas with RTM, we've got the wavelength, we've got wavefront healing, all the things that actually happen that we saw in those wavefront animations. All those things are corrected for in the RTM. So some of these things could end up being noise on a Kirchhoff section could end up being signal on an RTM section. So we're just feeling more of the wave propagation effects with RTM. It's just that we need to have such a velocity model accuracy and very high signal in order to reconstruct that wave field.
Okay, thank you. Here is the next one. The lack of imaging or illumination in the football blocks are just the result of the lack of source receiver offsets, or the trust fault can also play a role in the shadowing of the football blocks.
Indeed. So that's that shadowing thing that I mentioned with diverging rays and even the diverging wavefront. We saw that in the wave propagation animations for the RTMs, where sometimes you get the high velocity material and the wavefront actually separates, and we create these shadows, and that's a significant problem. And the only real way to do it, and actually in the question you have a bit of the answer there, is the only really way to do it is to sample the wave field more densely. And so I think the big thing is maybe not so much more sources, but more the receivers. And so if we tighten up that receiver spacing and we record more of the wave field, then I think then we can have that illumination from the shadows. One can hope.
Okay, it's okay. Here's the other one. Mm, Trustwell acquisition used to be expensive and complicated. Previous modeling indicates that high fall, 500, long offsets, 2000 kilometers, should be used for proper imaging of the subsurface. After costly acquisition, the processing shop with a decent PSDM routine can use a migration aperture of more than, say, 6 to 8 kilometers at the most. That's one example where the theory and practice it seems that does not work. Or what else it can be done in processing to make usable all that far offset recorded data?
Yeah, far offsets are tricky. Part of the problem with far offset recording is that the reflection at the reflector we can only have so much of an opening angle, and then you get past the critical offset and the amplitude to a string. Now in a foothill setting, you can definitely get further long offsets, 6-8 kilometers offset, maybe 12 kilometers is a bit high. But it's really not the aperture so much. I mean, 6 to 8 kilometers aperture is fine. The aperture, what you're doing there is you're migrating your data up to the steep dips. And by the time you get to 6 or 8 kilometers aperture, then you've got most of your steep dips are accounted for. It's just that you want to be able to have that aperture for all of your offset range. And by the time you get to a long aperture on a very long offset, that ray path length is so long, and that becomes so sensitive to velocity model inaccuracy that's where the practice becomes difficult because versus the theory, because the ray path length is so long, and all the attenuation effects of the energy and any little bit of velocity inaccuracy is going to be compounded on those long offsets and steep dips. So that's kind of the difficulty. So I'm not sure what we can do with that. Now we can use longer offsets in a foothills type setting in other areas because oftentimes we have very high velocities near the surface. So then we don't have the kind of the ray path going like this, going near vertical at the surface. Oftentimes our ray paths go out and go nice and wide, and we record these long offsets. And we can also undershoot mountains and other obstacles that give us difficult surface conditions. But there's only so much we can do here. It's a very good philosophical question as to how we can manage the theory and practice.
Yeah, for sure. Okay, it's okay, Rob. The next one. From the AVO perspective, which dataset should be more trustable? PSTM, PSDM, RTM, or neither of them?
Yeah, I think the more accurate, like when you look at it, you go to the swimming pool and you see the bottom of the pool, and it's like the light is making all these different patterns, right? And it's beautiful. But the thing that whenever you have these refraction effects, you have energy focusing and defocusing and that type of thing. So the same swimming pool problem where you see the pretty dancing lights at the bottom of the pool from the refraction. You have the same sort of thing with depth imaging. If you've got some refraction, then you're moving your amplitudes into some place where you may see it. It could be a velocity issue, it could be an illumination issue that results in this ABO response. So I think the more accurate your imaging, ultimately, the more accurate your ABO response is going to be because you've got your amplitudes in the right place spatially and in the right offset domain, or in the right offset for the angles, or in the right angle for the angle domain. So I think, in theory, the more accurate we have it is going to be better. In practice, they're also the more delicate processes. Mean if you've got your velocity model is inaccurate, you may be doing more harm than good with a more advanced algorithm.
Okay, great. Another one. How can you ensure a correct positioning of the bands in areas with no well information at all?
That is a really good question, and that's tough, and it is definitely a puzzle. And sometimes, for a TBI, we do all the imaging from the raw shot records through to the RTM and all the depth migration in between. And half of our projects go to depth. So all of our projects are time migration, and then half of those are depth migration. And there are two reasons that we don't do depth migration. And I guess it all comes down to one reason. And that one reason is unconstrained velocity. If we can't get a velocity model accurate enough to image the seismic data, then we won't see a benefit in the depth image. Now that sometimes we work areas that have no well information, but we've got a fairly good understanding of the local geology. There are a lot of cross section. The pre-sec time migration is a pretty good image, so we get a pretty good feeling for the velocity structure. And then even without well information, we can get a fairly accurate depth migration velocity model. And if we've got, because it's so delicate, because depth migration is sensitive, we can't say, oh, I want my target to be this big, and I'll put the velocities I need to make the nice big target. The imaging is just going to break down. With the velocity model that's inaccurate, the imaging is going to be weak. So there is that benefit to depth migration in the areas even when there's no well information. But if we have no well information, not much local geology, very complex structure, very weak imaging, which is again about half of our projects, then we don't recommend it. And sometimes we'll do a test of a 2D line to see how the data is going to respond in a certain area. And if we don't have enough constraints on the velocity model, then we'll have a weak image, and we'll suggest that we stop there and the interpreters use the time migration until they have more geologic data and well control.
Yeah, for sure. Okay. I think we have an extra one. Yeah.
Oh.
Hello. Are those numbers in the velocity model interval velocity or average velocity?
Yeah, so these numbers here, thank you for asking. That's a good one. I meant to address that at the time. So these are interval velocity, and they are the interval velocity normal to bedding. So then, because we have anisotropy, the velocity parallel to bedding, we assume is 12% higher than the direction perpendicular to bedding. So I'm trying to find a number that I could do in my head here. So if we've got 48. So here's an example: 4,100 meters per second is the velocity normal to bedding over here. So then parallel to bedding would be 4,480. Yes. Yeah, 4,580. Sorry, we had 480 to this one. So it's 12% higher in the direction parallel to bedding than perpendicular to bedding. So in this case, it's 4,100 in the direction normal to bedding, and 4,450, 4,580 in the direction parallel to bedding. I'm not good with numbers. That's why I was never an accountant.
Okay, no problem. There's no problem. Imagine us talking about numbers. Okay, so I think They are all the questions that we have for you. Thank you, Rob, again for accepting our invitation to participate in this webinar.
Oh,
Now I'm going to pass the microphone to our Vice President of the AAPG Young Professional Peru Chapter. I don't know, Leonardo, are you there?
oh,
Leonardo was the guy that established a contact with you.
thank you. Thank you for your
Hi,
message.
Rob. Good evening, Mr. Job, and all participants. On behalf of Young Professional and Six Student Chapter of APG Peru, I would like to provide a virtual certificate to Rob Vestrum, expressing our sincere thanks to his valuable time sharing his experience and this online conference, geological constraint seismic imaging of complex structures. I'm sure that the knowledge shared, shared in this conference will be great help to the participants. Help. Thank you, Rob, for your conference.
Thank you. That's very nice.
Thank you, Rob. For sure, we are going to send you this certificate by email. So you are going to have it for sure. Uh, Thank you, Rob. I hope there is not the last opportunity to have you here in Peru presenting your work with us and sharing your work with us. So, see you again in the future and have a good night. And in addition, I have to say to many thanks to all those attending this presentation. Do not forget to follow us in our social media networks in Facebook, YouTube, LinkedIn, Twitter, Instagram. We are going to put this presentation there so you can see the presentation whenever you want and wherever you want. So see you the next time, guys. So have a good night. Have a good night, Rob.
Thank you. Good luck to everybody.
Bye. Bye, Rob. Bye, guys.
Bye, Rob.
See you the next time. Bye bye.